Hello and welcome to another video from Ellensburg Amplifier Repair and Service. My name's Todd and today we have a Taramps Bass 15K in for repair. This has a failed power supply section. It had transistors that were burnt on both sides of the amplifier, so I have removed them. They are the IRF 1404s. So I removed those and now I'm working on the gate circuit. So what I'm going to do is I'm going to go through and I'm going to check the resistance values of the resistor. So let me get my meter set up here for you guys. Alright, so we have the meter in the upper right hand corner. Is it working? Yes. Alright, so as I said, I'm working on the gate circuit. So I got all the burnt transistors pulled and now I'm going to check the gate resistors. So you're going to see that we're 4.9 ohms, which these are says on the resistor 4.7 ohms. So 4.9 with my 0.2 tolerance on the meter is 4.7 ohms. That's what I like about Taramps. They do use precision resistors in all of their circuitry. So I'm just going to go along and I'm going to check the value of the gate resistors. And note any resistors that are out of tolerance. Oh, so here we have 123.7 ohms. And I'm just going to make sure that it is the gate resistor. So I'm going to check the one side of the resistor to the gate pad. We're 0.2, so that is the gate resistor, which, as you can see, is 124.89 ohms. So that is incorrect. That'll have to be removed. So I'm going to go ahead and mark the board to indicate which resistor needs to be removed. And I'm just going to continue on down the line. 4.9, perfect. And then I'm going to check the pull down resistors. There's going to be a pull down resistor for each bank, I should say. So you're going to have two pull down resistors because you have two circuits driving this. So 1.2K and the other one 1.2K. So this side just has one bad resistor, which we will remove. And then we're going to move over to the other side. Sorry for the reach around the camera here. 3.6K. Now that is obviously not correct. So we're just going to move right on down the line. 275 ohms. 339 ohms. 104K. Looks like we may have multiple resistors, or we have a shorted drive. So I'm just going to check the gates off. 4.9 ohms, so we got one good gate resistor there. 119, 170, and then 280. Let's check the pull downs. The pull down is 0.87 ohms, so that more than likely is a shorted pull down resistor. Where's my other one at? It's hiding somewhere over here. Oh, right here. So here's the other pull down, 0.52. So those pull downs are either shorted, or they have to be shorted because they go from the gate drive to ground. So what I'm going to do is I'm going to go ahead and remove those. So I'm going to fire up my ST862D hot air gun here. Set up 40% at 460 degrees Celsius. Yeah, I like it hot and quick. Hot and quick is the easiest way to pull resistors off boards here. Just like that. It takes 2 seconds. See a lot of questions about temperatures and air settings. Well, what I can suggest is that you just get a board that has SMD components and just start pulling them off and see what temperature works best with your style of repair work. So this gate resistor pull down is 4.7K, and this one was 4.7K. So the two resistors that I pulled off are good. Yes, so our gate drive seems to be shorted. That's unfortunate. Let me just do some more double checks here before I pull the drive IC. See, these numbers are all over the place, and 4.7 ohm resistors, usually if they fail, they'll fail open. They burn right open, kind of like a fuse. Excuse me. And none of these physically have burnt open, which is telling me that this gate drive is shorted to ground. So the gate drive itself is 0.8 ohms to ground. So, which again goes back to these SMD resistors that, like the ones I just pulled off, they physically will look burnt more than likely if they have failed. And they did not look like they were burnt, but I pulled them off because they're the easiest to pull off first anyways, just to isolate the gate drive path to ground, just to isolate that, which will allow you to test your gate resistors without having to take into consideration you have a resistor to ground. So I'm still showing all these oddball readings. I am going to just go ahead and pull the gate drive IC because I see no other reason why. The 10 ohm snubbers are still good. So these are resistor capacitor snubbers here. So which reduces your noise. I'm going to go ahead and pull that drive IC. Again, it's the same temperature. I'm just going to preheat the board up a little bit right around it because there is an SMD capacitor right next to it. And I'm going to get my straight tweezers because it's easier to get in there and pull the chip off. Just like that. Quick and simple, 40% air, 460 degrees Celsius. And then I'm going to inspect the pads real quick here to make sure I don't have any pads that are solder bridged, and they are open. So what that does is it isolates the IC from the resistors that you're testing. Numbers are good. Snubbers are good. Let me just double check my snubbers here. Snubbers are good. 10 ohms. Okay, so I'm still showing that. Oh, the gate drive is no longer grounded, which is good, but I am showing I'm still showing the odd resistance values on the gate drive circuit. Why am I showing that odd resistor value? Oh, I have a burnt 10 ohm resistor. All right, another resistor coming off the board. So that is going to be, what is that? That's going to be the 10 ohms. That's feeding the drive circuit. I do believe I'd have to look on the schematic. I'm going to go ahead and pull this off real quick here. Oh, and it broke right in half, so that was definitely a failed resistor. Let's see here, what do we got now? I'm running out of items here that could be shorted to ground. Nope, alright. Could it really be resistors that have skewed completely out of value? 3.74. Let's go ahead and pull that gate resistor and find out. Alright, so I just pulled that first gate resistor off, and I'm just going to check the value of that gate resistor. Oh, look at that, 6.3K. It did. So these resistors, more than likely, all these gates have failed and skewed the resistance values. Yes, indeed. 0.25. 0.25. So we're going to go ahead and pull this one off. Sorry for my head in the way there. 0.25. Let's just go ahead and verify this. So the drive IC may be okay. Yep. Alright, so it looks like all the gate resistors are going to be coming off. That was 0.28 there. So I'm just going to go through and pull all these 4.7s. Yep. Alright. This will take just a second to do with this hot air gun, so we will fast forward right through it. Or maybe not even fast forward. Once you do this enough, you get this process down pretty quick. Now remember, I have two pull-down resistors that are floating on my table here. All the gate resistors are removed. Oh, almost all. All the gate resistors are removed. The two pull-downs are removed. Would be nice if I didn't lose the pull-downs. Hold on, let me see if I can find these pull-downs. $4701. Oh, I found one of them. 4701. So here's one of the pull-downs. And what's the rule of thumb for SMD stuff? Is they never land right side up. Have you ever noticed that with ICs and stuff? They never land right side up. 4701. So there's my two pull down resistors, which I want to keep anyways. So I will reinstall those two pull downs. And also clean up the pad area for the drive IC, which is hopefully still going to be functional with the shorts that it had. So I'm just going to reach right on in here and clean up the solder. Just to let you know too, on the pull down area, you may need a little helping hand with heat because it is on the ground trace. And then the other one, again, is on the ground trace. So I just use a little bit of hot air with the solder braid to remove the solder from the trace. So let's go ahead and add some of our good old flux here. I kind of use it as a glue to help hold things in place. And of course it also does help flow solder properly. We're going to grab that 4.7, put it back where it belongs, and grab this 4.7 and put it back where it belongs. And then what I'm going to do is I'm going to solder down the end that is not on the ground plane. Because then what I'll do is I will use the hot air to tack down the side that's on the ground trace. So we'll keep this back up just a hair. Just like that. And a little bit of solder to this one. Just like that. Easiest way to work with the large surface areas of the ground planes. 4.7K. And where did I just put that one? Oh, right here. 4.7K and 4.7K. That's exactly what I'm looking for. Right, I'm just going to make sure that I don't have any shorts on this. Perfect. 1, 8, 1, 0. Good, 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 good. All right, we're looking great. 100 ohms, yep. All right, so I need a new 10 ohm resistor. Let me double check this one real quick here. 10 ohms, perfect. Grab a new 10 ohm resistor. And let's get this 10 ohm resistor soldered onto place here. Of course, a little bit of flux. And we'll go ahead and solder this into place. Just like that. And again, clean off the flux. My goal is to apply power to make sure that the MCU has not been damaged by the short. Sometimes when you have a short in the power supply, and if it makes it through the drive IC here, it can make it back to the MCU, and that MCU is the heart of everything. So the MCU that's used in the base 15K is this by ST here, which controls every aspect of this amplifier. It is the heart, the brains of this whole thing. If that MCU fails, which is right, I will show you right here, this IC right there is the MCU. This outputs a signal back to the drive ICs. The drive ICs then, of course, swing the transistors for the transformers. If that MCU dies, this amplifier will not function. So that's my whole primary goal, is I don't want to do too much work, get so far ahead of myself, and then come to find out that I have a dead MCU. So again, that MCU is located right here on the board. That MCU sends the signal back to the drivers of the power supply, and then these drivers swing the transistors on and off for the transform. So if the MCU dies, no signal to the chips, no signal to the chips, no drive at the transformers. No drive at the transformers means a dead amplifier. So my goal is to see if I have a functioning drive signal, but I want to make sure that my unfortunately my drive IC is dead. No, 0.44. That's not very nice. 0.44. Oh, is it though? Hold on. Oh, what am I thinking? I'm on the other side of the gate. Oh, that's perfect. Okay. 0.44. But to ground 1K. Nope. To ground, I am still shorted. 0.4. Where am I shorted at? Drive. I think I'm gonna have to pull that. I think that IC did not survive this short. So, unfortunately, we're going to be replacing that. Let me double check my gate to ground. Yeah, that's what I thought. Okay, so the drive IC did not survive. It shorted to ground. Well, so that means I need to replace it. Luckily, we can do that. Luckily, we can do that. So, what is this drive IC? It is the It is the '98A 524A 98A 524A 8A. Let's see here. The 524A. All right, so it is the UCC 27524. Now this amplifier is probably one of the first that I've had to do that had a power supply failure, which is quite interesting. Usually these amplifiers don't have power supply failures, but just by reading the resistance value of the gate resistors, I'm thinking this was a drive IC failure. Got too hot, probably. Yeah, probably got a little too toasty. So I'm just gonna go ahead and reheat that center ground pad again. And solder it down one more time. Although it looks like I kind of missed. These 4 capacitors. There we go. Perfect. Beautifully well done. All right, so that IC is now soldered back into place. Let me get it back into view for you guys, of course. And let's check my resistance value again, of course, after I clean up the flux. Keep it clean, remember, keep it clean. So hopefully my good old trusty capacitor here is still alive and well, not too hot, perfect. And let's go ahead and check the resistance value one more time here. So gate drive to ground. There it is, 4.5. That's exactly what I was looking for. So now I should be able to check the pull down resistor should show my correct value. Where did I put those? .3. 4.3. So once I get the gate resistors in, you'll see. Oh, I do have that bad gate resistor on this side still. Also, we're going to go ahead and pull that while I'm thinking about it. Just like that. Alright. Alright, sorry, I had to take a quick break, but I am back with this 15K here. Sorry, let me get this back into view. Alright, we are working on that power supply. So, I was getting 1K pull down values on this side here. Sorry, the board's flipped around now. I was getting 1K pull downs here, and over here, you'll see that I have my 4.1K pull down to ground, which that's what it's supposed to be, because we have 4.7K resistors pulling the gate signal back to ground. I have to apologize. I assumed that the 1K was correct, but it's impossible for it to be correct. It must be early. I'm used to 1K pull downs, and I saw the 1K. I'm like, oh, it's correct. Well, it's not. The pull down value you should read on your gates to ground your pull down value, and then between your pull down resistor to the gate pad, you should read the value of the gate resistor. Now, if you go from your gate resistor, your gate pull down pad, your gate. So now when you go to your gate pad to ground, you should read your pull down values. Well, if you look on the screen there, you have 1.6885. Well, guess what, guys? The pull down resistors are not installed. They're sitting right off the camera, right off the side here. So we got the one side done, fixed. Gate drive wise, we got the pull downs in, because if you read from your gate signal, your gate, there's little pads here, they're marked A, B, C, and D next to your gate drives. So if you go from there to ground, you'll read your pull down value, 4.173K. And if you go to the next gate drive, gate B, you're going to read 4.187K. That's what it should be, because it's getting pulled down to 4K. Now, if you go to this side here, we're going to go to gate drive C and go to ground. We are 1.686K. And then we're going to go to gate drive D, and we are 1.686. So that goes back to another failed drive IC, which again, it's always hit or miss when you have failed gate drive ICs, because it is directly driven by this IC. If there's a fault in the power supply, it can work its way back to the MCU, which that MCU, obviously, you can probably buy the chip itself, but you don't have the firmware for it. It's just becomes a real headache if you have a bad MCU. Get a hold of me. I may be able to get a new MCU for you. That's where we're at on that. I'm going to replace another gate drive IC. So what I'm going to do is I'm actually going to pull that off real quick here and see what my values are after I pull that IC off. And another capacitor next to it that I don't want to cook. So I'm just going to make this quick and easy for this thing. Just like that. So I'm going to read my resistance value from the gate pad to ground, and you'll see that it's open and that it's open. I should read 4.7, I do believe, pin 2, 4.6, and pin 4, 4.6. So I should read on pin 2, 4.6, and pin 4, 4.6. Those go back to the MCU to do their job. So, looks like another failed drive IC. That that IC took off on me. I'm not sure if this was the one that came off of it or not. So let me get another one installed here. We'll double check the resistance on that. And what we'll do is we'll put some power on this and see if I get any form of gate drive signal. I'll be right back with you. Alright guys, so let's get back to what I was doing here. So I had to flip the board around again to get this thing worked on here. So I replaced the driver IC, got that fixed. I put the two pull down resistors back into its places, and now what we'll do is we will check the resistance. Is my meter still up? We will check the resistance from the gate path itself to ground. So now we're reading 4.6K on drive C and 4.6K on drive D. Perfect. That's exactly what we're looking for. So I'm thinking I should be able to apply some power and see a drive signal. At least start. You know, this is not a common thing that I get in. Power supplies are not a common thing that I repair here on these Taramps boards. So let me get some power here. And see if this agrees to give us any form of signal. I'm not worried about voltages, because without power supply transistors you cannot have rail voltage. So I'm just looking at the lights. And I do get a blue on light. So I should have drive on. Maybe, let me double check my thought process here. So there it is. Yes, so we do have drive. We do have drive. Let me double check and make sure I have drive on both, on all four. Remember, again, these are A, B, C, and D. So I'm going to start over here back with A. So A does, let me try to get it better. I think it's 20 microseconds is what I'm after. It's between 10 and 20 microseconds. And let me drag up my trigger there just a little bit. What I'll do, oh yes, so what I'll do is I will switch out my meter reading for you guys to the scope read. So let's go ahead and turn the meter off, turn the scope on. And show you guys how the power supply reacts when there's no transistors installed. All right, so let me make sure, let me get my OBS pulled back up here. You guys see the meter, or the scope I mean? Yep. All right, so gate drive A again, you'll get that brief pulse width there, really short pulse width. But that is what we're looking for, is that really brief pulse width. So I'm going to go to drive B, and there's that drive again. Very brief pulse width. Drive C, and drive D. And we have all four power supply gate signals running the way they should. So that tells me I'm good to go ahead and reinstall all my 4.7 ohm gate resistors across the board here. The drive ICs are good that I reinstalled. And what we'll do is we'll get it all back together. I don't show any shorts on the output section, which is thumbs up. These use the, what are these? The GW 80H65s. So these are the 80H65 output transistors, the 1404 power supply transistors. Uses the, on the output side here, uses the SI8244 drive ICs, 2 of them. Again, if anyone has any connection to those, under my target is the average price that it used to be, around $12 an IC is what I'm looking for. I've been being quotes of as high as $37 per IC. So I have very limited supply of these left. I'm buying them in groups of 5 through one supplier. Every now and then I can catch their deal of 5 for $65. So that's how much I've been having to spend on these SI8244s. So that's where we're at on this. I do thank you guys for watching. I just wanted to go over a power supply repair of a Taramps board that I normally don't do. It's usually the output section that has failed. But this is the power supply section. Again, I don't have a affirmative or a confirmed reason why it would fail like that. I don't see any signs of reverse polarity. Could be an overload, but usually on an overload I'll see something on the output section. Again, this could be just failed drive ICs. Seeing how every bank had a shorted transistor or a blown transistor in it, and both drive ICs was shorted. One drive IC was shorted completely, which I would expect on the bank that had failed the hardest. But this drive IC also had a 1 kilo ohm short across it. So it's hard to say why this power supply failed. So I do thank you guys for watching. Please, again, if you guys are working on amplifiers and you're dealing with potentials that are abnormally high, again, these will run. These are rated at 250 volts, so you know you're going to have or expect to see about 200 and so volts DC on one side. Now you put your fingers across this, then you're going to have a huge potential, of course. So again, keep your fingers safe, keep your fingers out of the rails, and we'll catch you on the next one. Thank you for watching.